So we looked at sine and cosine trig functions. We're going to combine them together and we're going to form a new function, tangent. And we're going to look at the unit circle again, make sure we fully understand the unit circle for the sine and cosine terms. We'll build upon that and connect those concepts with the tangent. And we'll use the same logic that we looked at in the previous video where we were able to manipulate sine, looking at the period and the frequency and the amplitude. And we're going to use similar concepts and apply to manipulating a tangent graph. So before we jump back into the unit circle, we can look at a right triangle again to help us define the tangent term. Remember that we looked at sine and cosine in terms of the opposite side or the adjacent side and the hypotenuse ratio. Tangent is defined not with the hypotenuse, but just with the opposite side and the adjacent. So if we're looking at theta, then the opposite side would be b and the adjacent side would be a. So that ratio would be b over a. If we're looking at the angle phi, the opposite side would be a and the adjacent side would be b. So then we have AB. So this is the equivalent of saying that tangent is sine over cosine, right? So remember sine is, so for theta, right? Sine is opposite b over hypotenuse c, so BC. Cosine of theta is adjacent a divided by the hypotenuse c, so AC. So this hypotenuse terms cancel out and we just left with BA. Similarly with tan phi, you'll get the same thing here, right? Because sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. So if you divide these two, then you just get opposite over adjacent, which is how we define the tangent term. So we can define sine and cosine and then solve for our tangent, or we can go directly to it. So we can use a unit circle again to help us define the tangent term. A lot of times it is convenient to just think about it in terms of sine and cosine and just take the ratio of those two. But I leave it up to you how you want to work through it. Whatever makes more intuitive sense to you is the way you should go through it. So in the previous video, we looked at angles, specific angles for sine and cosine, and that's what's these first three columns are showing. This fourth column is including the tangent, and we can solve for the tangent by looking at the triangles associated and using the unit circle and this segment of triangles within the unit circle to help us figure it out. Or we can just use the ratio of sine and cosine as we defined earlier. Now, if we want to look at the unit circle, we can divide opposite over adjacent, and we define that as y over x. Now, it's important that we define the angles correctly. We've done it for 0, 90, 180, and 270, right? Here, 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 and here, and 360, right, which is 0, or 2 pi. And we've done it for the right isosceles triangle and the split equilateral triangle in here at 30, 60, and 45 degrees. Now, there's just one thing to watch out for if we're looking at quadrants 2, 3, and 4, that we're making sure that we're using the right angles when we're looking at this. And I'll briefly talk about it right now, and then we'll talk about it a little bit more as we expand this table. So a couple things to note. We have a couple 0 points, right, at 0 degrees and at 180. So whenever we're on that positive or negative x-axis, we get a 0. That makes sense from the perspective of ratio of sine and cosine because sine is equal to 0. So 0, when 0 is in the numerator, you expect to get 0. It also makes sense from the perspective of opposite over adjacent as a definition of tangent is, because the opposite would be the y value, and the y value is equal to 0 along this x-axis. And then you have the ratios 1 at 45 degrees, right? 45 degrees represents the right isosceles triangle. So from the perspective of sine cosine, those are the same values, so that makes sense. And if we're looking at the triangle, it makes sense as well because you have A and A as your lengths, right? The opposite is length A, and then the adjacent is length A. So those are the same lengths. So you would expect to get the same, or the ratio will be equal to 1 there as well. Now there's a strange one that shows up here at 90 degrees, or pi over 2, and at 3 pi over 2. So along the plus and minus y-axes. So for cosine, along this axis, our cosine value is equal to 0. That makes sense because our x value is equal to 0. And cosine is defined as x because it's your adjacent side, right? But for tangent, it's sine over cosine, right? Y over x. So you're dividing by 0. So it's undefined. So for tangent, we write plus or minus infinity for these. This is our vertical asymptote, which means that we go to infinity both in the positive and negative direction, depending if you're slightly below 90 degrees, going towards 90 degrees, or slightly above 90 degrees, coming back towards 90 degrees. And we'll see in the graph what that actually represents and how that actually shows up. Because tangent does oscillate, but it oscillates in a very different way that sine and cosine do. And we can look at things like the period. We can look at things like the effects of changing the amplitude and phase shift and frequency, and like the baseline from the same concept that we looked at the sine function, but it shows up in a different way. All right, so the last thing I want to talk about here in this slide is what I was talking about in terms of the angle when you look at a different quadrant, outside of quadrant 1. So when we're looking at quadrant 1, we can basically place these triangles here, and then the angle will be the angle down here. But if you're looking, let's say, at 90 degree, above 90 degrees, let's say you're looking at a 30-degree angle above 90 degrees, you would not want to use this triangle, right? You wouldn't. You want to use that right triangle. Instead, you want to use this right triangle, right? That looks basically like this one. And in that case, the angle you want to use is this one right here, which is a 60 degrees. And so you would want to reference this form or flip this triangle around so you're looking at the 60 degree, even though you're saying 30 plus and 90. So it's a key thing to recognize. And then you would have a negative x component, and then you would have a positive y component. So key thing to think about as you're building, and we'll discuss this a little bit more as we expand this this table to include 30, 45, and 60 degree increments within the other 3 quadrants. So here is one cycle of our tangent graph. And a couple things to recognize is you're going from a negative pi over 2 to a pi over 2. So tangent, this is a graph of tangent of t. This has a period equal to pi. And I know the table is going from 0 to 2 pi, so we'll show that too. But really, we're going from negative pi over 2 to pi over 2 for the time, or the x component, whatever you define as your x-axis piece there. We're crossing 0 at 0. That's this segment here. We're continually increasing. And as you approach pi over 2, you're approaching infinity. And this is one cycle. So this segment gets replicated over here. So on the right side of pi over 2, just a little bit over 90 degrees, you're at negative infinity. And then you're growing, right? That's what this segment is showing. Negative infinity, growing until you hit pi and you're at 0 again, just like here. And so we can show it replicating here. Let me erase these lines. Right, so this is a segment where we're looking at negative pi over 2 to pi over 2. That was this one cycle. And then you see it replicating over here, and then here again, right? So you're going up. So as these are your vertical asymptotes, the dashed lines are showing that, right? As you're going to pi over 2, you're growing, and then you have undefined at exactly pi over 2, and then as you're slightly above pi over 2, you're at a negative infinity, growing again up until you hit the x-axis. So you see this very, very different graph than we saw from the sine and cosine form, which also oscillated. So here we have sine and cosine, sine in blue curve and cosine in the green curve. And remember, whenever the cosine crosses the x-axis, whenever it has a 0 value, that's when we have this undefined or this vertical asymptote, right? So here, a vertical asymptote. Here, a vertical asymptote. Remember the sine and cosine, these are sine t and cosine t. This has a period of 2 pi, right? From here to here. Whereas your tangent has a period of pi, right? So from between the vertical asymptotes. So there is a significant difference in the behavior of tangent compared to sine and cosine because of that. But there are aspects that we can try to relate the two. So we're going to try to expand this table and look at how the graph and the unit circle will help us to expand this table. All right, so here is the full expanded table. I have for each of the I separated the table for each of the quadrants, and so we fully already looked at a number of these, right? At 0, 90, 180, and 270 degrees. We've already looked at those. We've seen the 0 points at pi, 0 and pi, and then we've looked at the vertical asymptotes at pi over 2 and 3 pi over 2, right, which are shown here. This is basically a shifted segment of the previous graph where we had this as our origin, basically this point here. So we're just shifting it so we can look at from 0 to 2 pi, which is a little bit more common to look at for a sine cosine. For tangent, realistically, we should be looking at this from negative pi over 2 to pi over 2, but it's the same. And this captures everything. All right, so this segment this first quadrant we've already seen. What I want to point out is from this quadrant to this quadrant here, which is your third quadrant down here, we have a negative x and negative y values. You see your sine values now turn negative because of the negative y component. The cosine values have a negative value because of the negative x component, right? Other than that, this is a repeat of this segment here. Tangent is just a ratio of sine and cosine, right? Ratio of x and y. So whether it's in the quadrant 1 where it's positive x and positive y, it's a positive value. Over here, it's negative x and negative y, but since it's a ratio, it's also going to give me same positive value. Right, and we can see that, right? So this is from 0 to I guess pi over 2, right? So this goes all the way up to 90 degrees, and so that's this segment here. So that's positive values, and here we're going from pi 180 degrees all the way to 3 pi over 2 or 270 degrees. That's this segment here, which are showing us positive values as well. Now, there is kind of a flip, right? Remember I was talking about, right, when we're looking at 120 degrees, this is 90 degrees plus 30 degrees. We don't just take these values and replicate them over here, right? Instead, we actually take the 60-degree values and bring them up here, recognizing that there is a negative x, we're in the negative x, positive y quadrant space up here, and that's why the cosine terms are negative and the sine terms are positive. So try to draw the triangles that represent the 120, 135, and 150, so you can recognize that. For 135, because it's 45-degree angle that you're drawing here, it's the same because it's 90 minus 45 degrees is 45 degrees. That's why these are the same there. Because of the sine value is positive and the cosine value is negative, our tangent is going to give us a negative value for this segment here. And so this is represented from pi over 2 to pi, and that's this segment right here, which give us negative values. Similarly, in quadrant 4, when we have the 270 degrees from the negative y-axis plus some angle, we're actually going to take 90 minus that angle to build our triangle. So similarly, like for 300 degrees, we don't take the 30 degree, we take 60 degrees. And those are our sine cosine terms. Now, because we're in the negative y, positive x quadrant, our sine terms are going to be negative and our cosine terms are going to be positive. And similarly, our tangent ratio is going to give us negative values. And that's shown here from the 3 pi over 2 to 2 pi region. So take some time. You know, I know I'm saying a lot of information out there. Draw the triangles in each of these quadrants to help convince yourself that this table is correct. The way to look at it is build your triangles that right isosceles. Look at the ratio of the sides and the hypotenuse if you're building your sine and cosine terms, or just the adjacent and the opposite for the tangent terms, and convince yourself the signs are correct and the ratios are correct, right? And just use 30, 45, and 60 degree increments off of each of these different axes to help you get this concept. Because once you get it for this set of tables, you can do the same thing for any other segment. And you'll always have your calculator, so you can calculate it to be sure as well. So the next thing we're going to look at is the same thing that we looked at for the sine equation. How do we shift this tangent curve? And what does it mean when we multiply or change the function itself? What will this function look like, right? So for here, I should have written it down. Let me write it down before we switch from this slide. These are all tangent of t or tangent of x graphs. But I can change things about this function to change the period, change the shape of it. So let's take a look at what those changes are represented as. Just like the previous video when we looked at the sine function, we can tune the tangent function. And so I set it up in the similar way. And a lot of things are very, very similar, right? Omega is going to affect our frequency. Phi is going to change the horizontal, the phase shift. We want to set it up as omega multiplied the quantity t minus phi so that we take into account the differing periods that omega might be creating. And so how phase shift affects it will be different. So that's why we're going to set it up this way too. And I'll show you the effects of that just like we did in the previous video. B is the baseline. For our case, it's the same. It's similar concept as when we looked at the sine function in that we're looking at from the tan t, right? Just the baseline tangent of t, the baseline we're saying is at 0, and we're shifting where that 0 point is when we add a coefficient here. The main thing that's different is a, right? So in sine and cosine, we have peaks and troughs, and we subtracted the 2 and then divide by 2 to get our amplitude A. We don't have peaks and troughs in tangent, right? We go from negative infinity to positive infinity. It's a different behavior, but I'll show you in a second what varying the amplitude or this A constant actually does to this tangent curve. So I'll show you a set of graphs just to give you some context. And remember, the purpose of doing all this is at least twofold. There's probably other applications, but the two that I can think of right off the top of my head is if you're trying to get a certain response from a system and the system is not responding exactly the way you want, and so you want to tune it. So if you have control systems, depending on what you're actually measuring, that can control A, omega, phi, or the constant coefficient B, that's great, then you tune it. Or the other option is if you have two systems, whether it be two experiments or two completely different physical systems that you're comparing, and you're looking at the responses, and you're comparing responses in this tangent graph form, you can look specifically at the difference in the A coefficient, omega, or any phase shift between the two, or any baseline shift, and try to give it physical meaning. That's very, very useful. So as we look at examples where these trig functions show up, the shifting and tuning is very, very important, and can help us make sense of what the difference between systems are, or how to design systems. All right, so let's first look at this coefficient A term. So in this graph, I'm using tan t as my baseline graph. That's the one shown in red here, right? So we see that for each of these three graphs, I have vertical asymptotes at negative pi over 2, pi over 2, and then it repeats itself, right? So the only thing that's different here is this B coefficient. So for blue, I added 2, the number 2, right? So from the 0, I'm shifting up 2, and the whole graph shifts up. For tan t minus 2, the green graph, I shift the whole graph down, right? So from that perspective, that's the same thing that happens with sine and cosine when we add it, right? Which makes sense. Here we look at that amplitude A coefficient term. So for that blue graph, I multiply it by 1/2, and you can see that, so the red graph is my tangent t, my baseline. So it's like you're grabbing segments of that and pulling it a little bit closer towards the x-axis. So this segment is pulled up. On the positive side, the segment is pulled down. And that makes sense, because whatever the value is, you multiply by 1/2. So if it's a negative value, you make it a smaller negative value, or like closer to 0, right? If it's a positive value, you make it a smaller positive value, closer to 0. And then for 2 times tan t, you're pushing it away from the x-axis, right? So you're making the curve, further from the x-axis, as you can see here, right? So the value, you multiply that by 2, whether it be negative or by positive. So I think those two are relatively intuitive. What about this one, the omega value? So because I tried overlaying all three graphs on one, and I think it gets a little confusing. So I separate the two here. So I have tan t in red in both cases, and then in blue over here, I have omega of 1/2, right? And you can see that the vertical asymptote for the red graph, the baseline graph, was at negative pi over 2 and pi over 2. Now it's shifted. Now the period has expanded, right? So remember, the period t is 2 pi over omega. So it's over 1/2. So the period is doubled with this omega term. So now we're going from negative pi through pi. So our period is 2 pi. In this green graph over here, we have tan 2t. So omega is equal to 2. So we cut our the period in half, right? Because 2 pi over omega. So we cut it in half, at least in comparison to tan t. So the vertical asymptotes, so I put in the dashed lines for the baseline graph. That's at negative pi over 2 and pi over 2. And we see for the green graph, we have it going from negative pi over 4 through pi over 4, this segment here. So it's cut in half. So omega directly impacts the frequency and the locations of your vertical asymptotes. What about phase shifts? So first, I did not account for the omega, or I chose omega equal 1 and just look at the phase shift. That's what we're showing here. So tan t in red, and then I do a phase shift of pi over 2 and a phase shift of pi over 4. And so the same thing. So I look at the graph. So let's look at this green graph first, right? Shown here. If I look at where it intersects the x-axis, right? Your 0 point, that's right here. That's at pi over 4. So if I grab it and shift it back to the left, pi over 4, the graph's going to overlap. And similarly for the blue graph, pi over 2, I grab that point and shift it by pi over 2, the graphs will overlap. So the phase shift occurs in the same way as we looked at for the sine and cosine graphs. And then here we looked at setting tan 2t as my baseline and looking at the effects of phase shift here. So the interesting thing is, again, you can stack these graphs. So tangent of 2t is the same thing as tangent 2t minus pi with an omega value of 2, just like as we shown in this graph here. We cut our period in half, right? So 2t minus pi, we can factor out the omega term, and this is tan 2 times t minus pi over 2. So your period is cut in half, so it's pi over 2 instead of just pi for tan t. And so this will overlap because you're shifting it by an entire period. So it's exactly the same. This is the same thing that we saw when we're looking at the sine component. And over here we have tan 2t minus pi over 2. The phase shift is not pi over 2, right? So to actually determine the phase shift, we say tan 2 times the quantity t minus pi over 4. So the phase shift between tan 2t and this green graph is pi over 4. So if I go to pi over 4, I see that that's where I intersect the x-axis. If I grab that point and shift it to the left, I'll overlay those sets of graphs. So again, I know it's a lot of information, but it's the same concepts, right? Recognizing and playing with graphs and seeing how A, omega, phi, and B affect it. And we'll play around with actual applications when these tuning mechanisms are important.